That's recording. All right. So we had this idea that when you have data coming in as sort of group and observation, and say there's two groups A, B, and for this person in that group, they got a 1 in that column. This person, they get a 1. This person, they get a 0. This person, they get a 1. And this person, let's say they get a 1. This person, a 0. This person, a 0. And this person, a 1. So in theory, you've got this long list of cases from each group. Each case has a group label and sort of an outcome label. And you might be interested in is sort of the rate at which whatever this thing encodes, so whether somebody died or not, or whether they responded to treatment or not, whatever this 1 and 0 encodes, you might be interested in ascertaining whether the rate at which this event happens is different between these two groups. So we could actually just look at, okay, what is the rate in this group, so we can compute the proportion of 1s, so that's going to be 75%. So proportion is 0.75. If I looked at this one, the prop is 0.5. But those are just like sample, the descriptors of our data. We want to know if we were to, what we should believe about the sort of underlying populations from which this data were sampled. So we went out and sampled 4 people, did something to them. We want to know if we were to do this sort of many times across many people, what should we believe? What is sort of a credible belief about not only the proportion in each group, but also sort of critically the difference between these two proportions. So we have these observed values, but we want to know is, given sort of the amount of effort we put into for observation, how credible is the difference between these two observed values. So you could, in theory, let's see, make a generative model that deals with talking about, okay, what is this group's underlying mean proportion, and maybe this other group's underlying mean proportion. But that tends not to be super common in the literature. It's a little bit complicated to explain, but it turns out proportions don't behave very well statistically. If you imagine going out and observing the proportion at which, say, people die in, you go out and you run one trial and you ask, what is the rate at which people die in this population? And then you go out and do the same trial again and record another proportion. And you keep doing that a bunch of times. The distribution of proportions that you observe aren't normally distributed. They also, the amount of variability and how sort of skewed those proportions are end up differing depending on what the underlying proportion is. So if you had a scenario where you, again, on this is the proportion, if you have sort of a true proportion of, in the population of 0.5, you'll get a nice, actually normally distributed thing around 0.5. However, and this distribution is reflecting the observed proportions if you went out and you did that trial thousands of times. However, if you had I'll stick with this. If you had a population whose true proportion is like 0.9, you're going to get, again, sort of a peakish around 0.9, but it's going to be this weird negatively skewed distribution, and if you had a true of 0.1, it's going to be this weird positively skewed distribution. The amount of sort of variability in each is also going to be dependent on how many people you have measured in each of your trials. So for various reasons, the proportion isn't a very good sort of measure or to use to talk about then differences between groups, because you have this sort of skewness and bias in how you end up observing the group level proportions. However, if we actually, instead of do proportions, we talk about the log odds scale, all of these end up having nice normal distributions. Now, 0.5 maps out to 0 in log odds, 0.9 is going to map out to some really big number, like 100 or something, and 0.1 is going to map to some other number. Notably, it's symmetric around 0, so sort of a shift of the distribution. So here, the peak is at 0.9. That's about 4 units, 0.4 away from the 0.5. So it gets up to 100. 0.4 this way away from 0.5 ends up being the same amount of distance on the log odds scale. So there are I don't expect you guys to really understand or know why we use the log odds scale a lot. It's actually just to sort of accept that it's a common thing to use. But one thing I do want to convey is, for those of you used to the idea of a odds ratio, when I have, so let's talk about, first of all, a proportion is just sort of the mean of those 1, 0, 1, of the ones and zeros. That's what a proportion is. The odds is the same as, or is equal to that proportion divided by, so let's call it proportion 1, proportion outcome 1 divided by proportion outcome 0. So the proportion of times that it comes out 1 and versus the proportion of times that it comes out the other thing. Another way of phrasing that is, when you know it's binomial data, is proportion 1 divided by 1 minus the proportion 1. So if you had, say, the scenario of 0.75 for group A, well, actually, just let me express the last bit. So we've got probability and log odds is just the log of P1 over 1 minus P1. Okay, so let's take an example of that proportion that's 0.75. So if P equals 0.75, then the odds is equal to 0.75 over 0.25. So that's 3. So you're 3 times more likely to get a 1 than a 0 in the in this data. That's what sort of the interpretation of odds are. You've got a 3-to-1 rate at which the ones occur. In contrast, let's take the other group, which had a proportion of 0.5. So if you've got P equals 0.5, then the odds is equal to, well, 0.5 over 1 minus 0.5 equals 1. Okay, so 1 means that you're 1 times more likely, or you're equally likely to have an outcome of 1 than an outcome of 0. So it's a 1-to-1. So odds actually end up being talked about more because people in their discussions like to, it's a little bit easier for humans to conceive of the idea of odds, rather log odds. But the actual analyses end up being on the log odds scale. And you know that because when you end up talking about a comparison, say we've got it, this one group has an odds of 3, the other group has an odds of 1. What's the sort of the metric used? You could say, okay, what's the difference in odds? So 3 minus 1, you could talk about it as 2, but more commonly talked about is the ratio of these two things. So you could talk about it, you're 3 times more likely in one group to get a 1 than the other. So it would be 3 divided by 1, and so that equals 3. A ratio of odds. Let's step back and talk about just what is if you've got A divided by B, and you want to know what is log of that thing, A divided by B. Anybody remember your high school math using logs?
I think that should be log A multiplied by log B.
Is it multiplied?
Oh, sorry, blind.
Aha. Yep. So this is the same as log A minus log B. So a difference on the log scale corresponds to a ratio on the raw scale. So this whole time when we are doing our code and we've got that diff, usually we have Bernoulli logit, and then a thing on the inside that is, say, mu plus diff IFF diff times x, and then actually that's all we have in there. Again, this difference parameter is establishing sort of the magnitude of the difference between two groups. X contains just the column of indicator, which group each observation comes from. This Bernoulli logit is just saying that what's on the inside here is taking place on the log odds scale, and when we say y is distributed as Bernoulli logit, it's saying, okay, this is happening on log odds. That determines a probability that then is expressed as a 1 and 0 outcome. That's sort of flipping the coin. So this diff as a difference between log odds is an odds ratio. So you just would have to exponentiate the diff parameter to get out what the odds ratio is for the data. So let's actually, it'll be clearer if I actually walk through one of our original examples from the other day. All right. No, it isn't downloads, binomial. All right, so I'm going to go through example 1. Oh, I have this open already. Oh, no. I put permanent marker on the screen of this computer, which is not mine. I'm pretty sure I can find a solvent that will. Yeah. Okay, so I'm going to close this RStudio and open up a new one. So I opened this up by clicking on that file. It'll open a file. It'll set the working directory. This was what we ran through the other day. So it's this data frame dat where we've got 2 columns. Say it's from a drug trial, and the column indicates whether they died or not. So why am I writing this data out? I think that's because I was, oh, yeah. So if I want to just look at the overall rate at which this found, library dplyr, and then, so we had this data from before in the drug group. There was a lower overall rate. Again, those proportions are the same, or those are the proportions that are just measured in each group. So I think this is 0.7 and 0.9. In our fake example over here, I had 0.75 and 5. So when we observe these proportions that sort of happened in the sample we have, we want to do inference on whether the actual populations that we want to refer to have a difference. So we need to create that sort of indicator variable column. So we went through, we created the group as num as a column. So if I look at that now, it's got a third column, which everywhere there's drug in the group column, there's a negative 0.5, and anywhere there's placebo in the group column, there's 0.5. Compile the stand model. While that's going, I'll go over and take a look at it. Oh, it's not going to open until it's compiled. Let me see. Do I have... Just opened it up in something that's it's not going to show the nice syntax highlighting, but stand file, 3 sections, data's coming in. We have to tell it sort of how many observations we have, give it the column that indicates the outcomes, we'll call it Y, and give it to the column that we just created with the numeric indicator of what group people are in. But otherwise, we have that same sort of mu and diff parameterization. We're saying mu is sort of a prior centered on 0, and diff, again, is another normal prior centered on 0. With binomial data, there's no standard scaling that we need to do. 0 and 1 is a pretty broad prior on both a center and a difference, so you can stick with that. And then we had what I wrote down there. We're saying that Y is distributed as the outcome of a Bernoulli trial, where the thing on the inside is the logit of the probability. So usually Bernoulli trials are parameterized by what is the probability of 1 versus 0, and this little underscore loaded is just indicating that whatever's in here, in order to get the probability, Stan will exponentiate this and convert from odds back to probability. So this is on the log odds scale, whatever's happening in here. And it's just sort of a standard regression, really, of the predictors. So we've got an intercept mu, so that's going to determine what the overall odds, log odds of the event happening, death happening. And then we also have this diff, which will express what is the difference between the groups in the log odds of the event happening.
So sorry, this is regression analysis?
Well, this is all regression, technically. It's going to look more regression-y, hopefully today, if we, as I walk through the multivariate example. Actually, it's just you're expressing an outcome as sort of a numeric formula. So far, x has only ever been like one vector, but you can actually have x as being a number of different predictors. X would be a matrix then with lots of columns, and you have to do something to sort of change up how you express it. But fundamentally, all these things we've done where we've said sort of there's a center and a difference, and we had an indicator variable for whether you go up the distant difference or down the difference from the center. This is all being regression. I just haven't bothered using that phrase yet. So that's our model. Hopefully, if I go back over to RStudio, it's compiled. And so the model is expecting data in where we say how many sort of observations there are. So that's the number of rows in dat. It's expecting this other thing y, which is an outcome. And it's expecting this other thing x, which is the indicator variable, the numeric indicator variable. So I'll run all this. I'm going to make this big and slide this over. So that'll go really quickly. And we get our outputs looking at the r hat and nf. R hat's above 1, nf is above 1,000. So we can look at the contents of this table. And the first line is just saying what the overall log odds are. So the overall log odds of the outcome are 1.35 with a credible interval of 0.73 to 1.97. If you actually want to convert that to say, okay, what is the overall probability of the outcome, so death, then you can use the p-logis function. Here I just wanted to convert just these numbers. So I said p-logis 1.35. That comes out as about 0.79. So you could say the overall probability of dying in these groups was 80%. But our credible interval ranges from 0.73 on the log odds scale, which corresponds to 0.67, a proportion of 0.67 on the proportion scale.
And so can you still give that as like a 95% credible?
Yep.
Converting from log?
Yeah, you can still do that. And 1.97 on the log odds scale, which corresponds to 0.88 on the proportion scale. So you could report it that way. If you are talking about this is the difference on the log odds scale. If you wanted to talk about the odds ratio, you would just take this and exponentiate it. So I'm going to copy 0.89, and the exponentiate function is just exp. So the mean odds ratio for the difference between the two groups is 2.435. So it means that one group is 2.5-ish times more likely to die than the other group.
Which group?
Well, we know that in the actual sample, the direction was the placebo group was dying more often than the drug group. So the you'd say the odds of dying are 2.5 times higher in the placebo group. You can express that credible interval still, so you take that 2.5 percentile of that difference and exponentiate that. So exp negative 0.17, and you'd grab the 197.5. So running those, you'd say the credible interval for the odds ratio is 0.84 to 7. So the odds of dying is, I guess, the credible interval for the for the difference between the groups in the odds of dying is from 0.84 to about 7. So so one group being 8 times more likely to die than the other is not very credible. Alternatively, one group being 0 times more likely of dying than the other is not very credible. So the idea, you can talk about this odds ratio. If you get an odds ratio of 1, that would mean they're equally as likely as dying, equally likely to die. That would be sort of the null hypothesis. So the fact that this credible interval includes 0 conveys that 0 remains a relatively credible hypothesis. Similarly, just the exponentiated version from 0.84 to 7 includes 1. Again, reflects that equal odds of dying between the two groups is still a relatively credible hypothesis. So that's for getting the odds ratio from the log odds, the difference on the log odds scale. Ghislain expressed that you guys might be interested in actually talking about what should we believe about each group. So up here, we said the observed proportion for this group is 0.7, and the observed proportion for this group is 0.9. So how do we convert the fact that the groups overall have a mean of log odds of dying of 1.35 and a difference between the groups of 0.89, how do we convert this back to expressions of what we should believe after the fact about the likely probabilities of dying in each group? So to do that, what you need to do is you need to say, okay, so for so whereas before I could just take the numbers that were in the table and either use this translation to get out the probability for the intercept, or use this to get to the from the log odds to the odds. So this will get from log odds all the way to probability. This one you can only get from log odds to odds. It wouldn't make sense to apply the p-logis to the diff thing. I won't go into why. But in order to express what is the probability in each group, we actually need to go and get the samples that the model has obtained. So these observations, this table, is actually a summary of the posterior samples it's obtained from combining the data with your prior. So you actually need to go get those samples. So if you say, let's call them samps, and if you say extract, I'm actually going to be explicit because I think there's another package with an extract function. So I'm going to say rstan : extract. And what did I call it? Out is the thing that we got from sampling. So if I create that, it's going to create an object that is a list, strsamps, of, actually 3 things. We can ignore the LP. So it's a list with one element called mu, which is all the samples for mu, and another element called diff, which is all the samples for diff. So if we want to talk about the drug group, remember it's the equation we had was whatever mu was plus diff times x. So x was -1 for, or sorry, -0.5 for the drug group. So we can express what the drug group P should be by, first of all, doing that little equation. So it's whatever mu is plus diff, whatever diff is, times 0.5, or sorry, times -0.5, because the drug group had a -0.5 in their column. Now this will get what the log odds are in this group, but we want to convert that back to an actual probability, so you just wrap it in p-logis. Now, I actually have said mu and diff here. Well, I'll just say mu equals samps mu and diff equals samps diff. So that just pulls these 2 items so I don't have to write samps $ all the time. So if that's the way to get the probability of dying for the drug group, I'm just going to copy that, paste it below, and say placebo P. So if the drug group was mu plus diff times -5, the placebo group is going to be mu plus diff times 0.5. So I'm going to run those 2. Oh, no, I didn't run this bit. 1, 2, 3, 4, 5. Sorry for that ... I'm getting notifications on my other screen that I can't remember how to turn off. So now we've got these two things, drug P and placebo P. If I look at drug P, it's a big long list of numbers. These are posterior samples for the drug P. So we need to actually summarize those samples. We can look at a histogram. So if we say hist drug P, it'll look like that. Maybe take a look at it with a couple different choices for how it makes the breaks. We can do the same for placebo P. Notice that drug P looks like it's a little bit further down this way, so we can't, it's hard with this visualization to really compare. Maybe if I set the axis limits. So x lim equals C0, 1. This will force it to have the x-axis be from 0 to 1 in both plots, making it easier to compare the two plots. Okay, so yeah, you can see like one distribution is clearly shifted relative to the other. And if we want like the credible intervals on those things, you can do that. So quantile is the function you use for the credible interval, drug P. There's an argument to quantile called probs, and that's the probabilities that you want. So we want the 0.025. Maybe we'll ask for what the median is, 0.5 and 0.975. So what this is saying is from our analysis, we can have a credible interval on the probability, that's sort of the true probability in the drug group that ranges from 0.55 up to 0.84 with a median around 0.71. Push this up there so people see it. And ditto, we can do the same for the placebo group. So their credible interval ranges from 0.72 to 9.94 with a median of about 0.86. So, I mean, one is clearly shifted relative to the other. But, I mean, if you just looked at these two credible intervals, they overlap by quite a bit, seemingly. But, so, like, if I were to just report these two things, it would seem that there actually wasn't much evidence of a difference between these two groups because there's quite a bit of overlap in the credible intervals. That's one reason that I didn't show you guys how to do this, is because those credible intervals on the individual condition means are not actually informative with regards to the questions that we're interested in, which is what we should believe about whether there is a difference between the two means. That's because when we create these individual things, drug P and placebo P, we're combining two parameters of the model, each of which we are uncertain about. So the uncertainty then that carries through to where each condition's mean is a combination of these two, of our uncertainty on these two other properties of the data. So obviously you're going to get larger sort of expressions of uncertainty in the predictions for each condition. So the fact that these two conditions overlap isn't surprising and doesn't speak to whether we should believe that there's a difference between the conditions.
So the median, the 0.71 and the 0.86,
Yeah.
they would just be expressed as the median probability of
Yep, yeah.
dying in either group.
Yeah,
And
and this
so-
is very close to actually what we observed in the sample. We had 0.7 and 0.9.
So in terms of what we would actually conclude from what we've done, if there's not that much point to using that test, then we just want to use odds ratios.
Yeah, yep. I'd express it either in log odds scale, as the sort of what's printed in this table. So there's a log odds difference of 0.89.
And that's
Or if you feel more comfortable with odds ratios yourself, you can talk about it using, say, there's an odds ratio of 2.43.
Could we learn a little bit about how some of these things would translate into non-Bayesian statistics? Just because we need to also talk to people who don't know what
Right.
this is.
The only thing that's going to be different from the non-Bayesian is the fact that we're able to establish priors on these two things. The typical way to do this actually saying Bernoulli logit and then having this sort of equation in here is the same thing as logistic regression. So the numbers you're getting out, if you were to do logistic regression, you'd actually get out something here that's sort of expressing whether or the value for the parameter in that logistic regression. Usually this would be called an intercept, and then this would be called, say, an effect. You'd get out, I don't know, you'd probably get out something that was like the probability. You actually probably would get a credible or a confidence interval on that. So you're getting out a lot of the same things. And indeed, if we were to have mu as uniform from negative infinity up to positive infinity, and diff as uniform from negative infinity to positive infinity as our priors, we'd get out a credible interval that would be the same as the confidence interval that you get from a traditional frequentist logistic regression. But we actually want to provide it with some information that, and that makes our credible intervals a little bit more, well, if you provide information that is actually reflective of your prior beliefs, then you'll get more accurate information in the posterior, and often that makes your analyses more powerful. So does that help at all? At least to give you some of the terminology.
Yeah, exactly. That's
Yeah.
what I don't have.
Yeah, so somebody that actually was familiar with logistic regression, if you gave them these sort of values, and either in the log odds form or if they wanted them in the odds ratio form, they would not really even know that you'd done it in a Bayesian way versus a regular way.
What if someone asks you about a p-value? What can you give them that's...
Well, you're not going to get anything out of the Bayesian way of doing things that's corresponding to a p-value. There is a mapping between sort of confidence interval and credible interval. But at least in my field, p-values are becoming less and less used anyway, and confidence intervals, amongst the people that aren't Bayesian yet, confidence intervals are becoming sort of the new hot thing to use.
So what
getting
would you
people to
say
be...
somebody?
Well, somebody that wanted a p-value, I'd maybe give them all the literature. So there's a large literature on why p-values are bad. I can maybe send you guys, there's a good sort of summary post on a site, stats.stackoverflow.com. I can send you guys a summary of it. It's a bibliography of literature criticizing p-values.
That'd probably be useful for.
Yeah.
So for question 2, when we're looking at the gold standard versus the new test, can we move on to that? Sorry, is that okay?
Yeah.
I don't want to monopolize the class. But essentially for scans, we're using the gold standard. We're using that as our X, like our predictor.
Yeah.
And then we just use Y. We just use the new outcomes for Y. So we don't need to use the negative 0.5 or positive 0.5 for anything, right?
You would turn the gold standard into a number that's negative 0.5 and positive 0.5. Because that allows you to, if you had it as like 1 and 0, that would make it so that 0 actually is also the intercept thing. So let's actually I've given up on talking about the multivariate stuff today. We'll talk about it on Monday. No. This is all stuff that's clearly I want to make sure that you guys are comfortable with. So, all right. So the center diff parameterization, if you have, say, group A and group B, and you have sort of the dot here and dot here, and this applies regardless of whether you're talking about binomial data on sort of this axis here or actually continuous data. So this applies to all the stuff we've done before with continuous data as well. The center diff, the way we had it, we said, okay, call A negative 0.5 and, and call B positive 0.5. If we're imagining that, that means that there's something in the middle called 0. And if you remember from like your high school math, fitting a line between 2 points is y equals mx plus b.
Remember something.
Mm-hmm. So do you remember what b was? The intercept. And so what does the intercept mean though? Like
Where it crosses the
yes. So b is where on the y-axis does the line cross hit 0. So by coding this as negative 0.5 and positive 0.5, we've made it so that this line formula is referring to the center point between these two things. And then by making it negative 0.5 and positive 0.5, the sum distance across this is 1 on this axis. So if we're talking about m is just the difference between these two things. Right? Does that make sense? If the thing, so m is rise over run. So if rise is this much and run is 1, it's this much over 1, which is just the same as this much. Like you don't have to consider the 1. So that's why I've had you this whole time having 0.5 and negative 0.5 versus negative 1 and 1 is because it makes it so that this the size of the difference just is 1. So when you talk about the slope reflects the difference between the two conditions. So let's imagine, though, instead we had, in the 1 minute we have left, a scenario where instead we still have A and B and 2 points, but we called A 0 and B is 1. Well, and we still want to talk about this line, so that's at 0. Well, that actually means that this equation y equals mx plus b is going to reflect this thing. So b sort of kind of reflects what what a actually is, like how high from the axis is this point for A. So that means that this other thing has to be, so if it's 1, how much does it rise from 0 to 1? So that also then is equivalent to saying what B actually is, or sorry, what M actually is. So this would be B and this would be M. That's the same as that original parameterization where we're just talking about two groups. They both have their own mean, and that makes it hard then to sort of place priors on the difference between the two means, and the difference between the two means is the thing that we're interested in. So that's why coding your predictor variable, so A and B, as 0 and 1 is a bad idea because it makes it harder then to set your priors on the difference and to talk about that. So that's why when you have this example of the data coming in, you should recode the gold standard test as negative 0.5 and positive 0.5, and recode your new tool test as 0 and 1. I know that's a little bit weird to have different numbers in the two columns.
So then we do basically the same thing as the other, and then we get an output with mu and diff.
Yep.
And so diff is how we, like, the discriminability of
Yep.
the test.
Yeah.
And so that's expressed in logic.
Yeah, it's still in log odds space.
Okay, log odds.
You can talk about it in odds ratio. Ideally,
And,
yep.
okay.
If the new test were unable to actually discriminate the two groups as determined by the old test, then you would get just chance performance, and it would be sort of an odds ratio of 1 or log odds of 0. Ideally, the new test actually does discriminate the two groups well, so you'll get a large log odds value and therefore a large odds ratio value.
And if it was a worse test, then it would be negative.
Yeah, although that you could just, if that were the case, you could just switch the labels, in which case it would be a good test. Like if it consistently called the diagnosis positive group negative and diagnosis negative group positive, you just would switch the labels and then it becomes a good test.
And then
Yeah.
my
So-
question though is, do we want a more sensitive or specific test? Like,
That's those numbers don't come out of what I've shown you so far.
Yeah.
I'm going to show you those next week.
Okay, so we just want to get the odds ratio.
Yeah.
Okay.
Yeah.
Okay. Thank you.
Yeah, sure.
All you want?
Yep. Sorry? Oh, no. Gotcha. No.
I sent you a mail.
Yeah.